This is good practice. This is, you need to be able to do these for sure. If you can do them easily, we can skip. But until, I'd like to see you be able to do these before I advance beyond them. So what's the first one? Number 9.
Would it be 1/7x times 7?
Good. Which, notice, 1/x. Which is very interesting because that means the derivative of natural log of x is also 1/x.
Mm-hmm.
So the derivative of natural log of any coefficient times x is still 1/x, oddly enough. That's a very unusual thing that I've always found interesting. Okay, how about number 10?
I went with 1/2x to the 8th times 6.
Number 10. We need the product rule.
So it would be x squared plus 1/x
times 1/x. In other words, it's u times v prime plus u prime v. You understand that when I write it like that, what that means?
Yep.
Okay. That's why it's times. It's because we're doing this part. Okay. Plus, now what's u prime v?
2x plus natural log x.
Not plus, times. You keep saying plus. You see why it's times? It's u times v prime plus u prime times v. These are multiplication here. That's multiplication. Okay? Now simplify that. What's that simplified to?
X
plus 2x natural log of x. And that's a good answer. I could factor out a greatest common factor of x, but there's no real reason to do it. I can't do anything else after factoring that out. Okay? About 11.
Is it just 1/x squared times 2x?
Yeah, it is. That's a good way to do it. Which, notice, that becomes 2/x. That's the answer. In other words, you always want to simplify it where you can. Notice another way I could have done this was I could have taken that exponent, 2, brought it down in front using the rules of logs so that it was this. Okay? And now when I take the derivative of that, I immediately get 2 times 1/x, which is 2/x. So I get the same answer regardless of which way I do it. Kind of like the way you did it because it was just a direct application of the chain rule, as opposed to having to rearrange it based on the logarithmic rules.
Mm-hmm.
Okay, let's make sure you can do one more. It looks like you understand these pretty good. What's 12?
1/2x to the 8th times 16x to the 7th.
Simplify that.
8x to the 7th over x to the 8th.
Simplify it further.
8 over x
There you go. Again, kind of illustrating that same principle. I brought the 8 out in front of that. Well, I know the natural log, the derivative of natural log of 2x is 1 over x. No matter what that coefficient is, it's 1 over x. So by bringing the 8 out in front, I'd have 8 over x. Not sure if that's easier or not. Still an interesting phenomena that the derivative of the natural log does not matter if there's a coefficient in front of it. Now, this one. Do you have answers on this?
Hmm?
Please have an answer for this one. Tell me what it is.
I have no idea how to do that one.
Well, if you have an answer, I'll be able to tell you. Can you look in the back of the book for the odd ones?
I don't have it on me right now.
Okay, because I'm not 100% sure how to handle the absolute value signs. Let's see, I guess, let's see if we can figure out how to handle this. In other words, if the sine x is negative, here's the sine curve. It's negative from pi to 2 pi. Then we're going to reflect it up to there. So the curve is going to look like that. That's what the absolute value of sine x looks like. And we're taking the natural log of that. Well, the derivative of the first part of this is cosine, and the derivative of the second part of it is the same thing. They're both cosine. So it makes me think that the answer has to be 1 over cosine of x times the derivative of cosine of x, which is minus sine, which is minus tangent of x. The question mark that I have is that I did it exactly as I would do it if there was no absolute value signs. And that's hard to believe that that doesn't matter. And that's why I wish I had an answer. So I would know. Maybe it's the absolute value of the tangent of x. I'm not sure. Normally I'd be able to look it up on Wolfram alpha. Let's try. That's the only one you're going to have problems with. You know how to do the others, I believe. And this time I think I know how to do it on Wolfram alpha. So what I need is the derivative of natural log of x. Derivative of, hold on, natural, here we go. No, that's natural log. No, that's just telling me the format I can use. So let's see what it says for that. Should say 1 over x. Okay. Now let's change it and put absolute value markers in there and see if it gives us a different answer. Now I need ABS of x. See what it gives for that. Okay, you'll notice it tells me what it's writing. Gives me the same answer. So that leads me to believe that, and here I'll instead of x, I'll put sine x in there, and then we'll have the problem we were actually doing. And it should say negative tangent. That is the problem, isn't it? Log of the absolute value of sine of x, and it gave me cotangent. How did it get cotangent? It's 1 over, oh, yeah, I did it wrong when I did it. I came up with, I erased it. But here's what I did. And it does give me the different sign. In other words, I did negative cos. I did 1 over sine times the derivative of sine, which is, no, it's positive cosine. What am I thinking? That's cosine over sine, that's cotangent. That's the correct answer. I made a mistake the first time I did it, having nothing to do with the absolute value signs. So according to Wolfram alpha, it does not appear to make a difference whether you stick absolute value signs around that or not. And in a way that makes a little bit of sense, because you cannot take the log of a negative number. You can only take the logs of positive numbers. So sticking an absolute value sign around it doesn't really accomplish anything. It makes it positive, but it's got to be positive anyway. We would not be able to take the natural log of sine of x when x was between pi and 2 pi, because it would be a negative number. And that has nothing to do with derivatives. It just has to do with logs, the rules of logs. All right, let's look at some of these more difficult ones that don't have absolute value signs, although now I know how to do that. So that you just ignore it. Assume they're parentheses, basically. Which one on here looks difficult to you? That you want? Which one do you not sure you know how to do?
14.
Okay. What rule are we going to use?
Motion.
Okay. So what is it?
X times 1 over x.
Now you got to apply the chain rule.
Wait, why?
Well, because here's what we have. We have a function that is u over v. Okay? And y prime is start with the bottom times the derivative of the top. That's what we're doing here. Only we haven't applied the chain rule to the derivative of the top yet. Because all we did is take the derivative of the outside to get 1 over x squared. Have to multiply that by the derivative of the inside, which is 2 over x. Notice all the x's disappear. So the left side of the top becomes 2. Now minus what? In other words, this part here simplified to 2. Now I still have to do the derivative of the bottom times the top all over the bottom squared. So I got to do the rest of it, but this 2 represents what I've circled on the left side here. That is v times u prime. Now what's v prime times u?
Wait, it's just 2?
I believe so. I did the math.
Yeah, I get it.
I start with the bottom. There's the, hold on. I start with the bottom. That's the bottom. times the derivative of the top, which is 1 over x squared, times the derivative of the inside, which is 2x. So I get x times 2x all over x squared, that's equal to 2. So that became 2. Now let's do the rest of it. What's v prime u? We're looking at this function right here.
Would it be?
What's v prime? Do it one at a time. Derivative of x.
So it'd just be natural log of x squared.
And the bottom?
X squared.
Here's your answer. There's your answer. And I don't think there's any way to simplify that. I could move that 2 down in front. Factor out a 2, doesn't do me any good. So that's as good an answer as any. Can definitely not do anything with that x squared, which is the argument of a natural log, and that x squared, which is a polynomial equation or a function. Okay. So what else? I mean, we can just go in order if you want.
Yeah, I just don't get 15 either, though. I don't know how to do that.
Which one?
15.
15? What rule are we going to apply?
Is it quotient then?
Okay.
Chain?
So it's the chain first, because we're going to take the derivative of the outside, right? What's the derivative of the outside?
Just
1 over, let's write in this color here. I like this color better. 1 over that fraction, right?
yeah.
Well, that means the reciprocal of that fraction. So it's not 1 over anything. It's x minus 1 all over x plus 1. There's your derivative of the outside. Now, we have to multiply that by the derivative of the inside, and in order to get the derivative of the inside, we have to apply the chain rule. So the chain rule, let's draw the most of the chain rule up. Okay, now let's fill in everything. What goes here? What goes where I'm pointing?
That would be x plus 1.
No, you start with the bottom. X minus 1 times the derivative of the top, which is
1.
minus the reverse.
X plus 1.
All over the bottom squared.
X minus 1 squared.
Now simplify the numerator, because a lot of it simplifies. What does that numerator become when I remove the parentheses?
It becomes x minus 1 squared.
No. When I remove the parentheses, I've got an x minus an x, so the x's cancel. And I got a minus 1 minus another 1, so that whole thing becomes minus 2. Okay, you with me? There's a lot of simplification that goes on here. That x minus 1 cancels with that exponent, and I end up with minus 2 as my only thing in the numerator, and in the denominator is x plus 1 times x minus 1. And that's my answer. These are not hard, they're just more steps. And that's the only thing about calculus, is as long as you have these 4 rules for differentiating functions, I can get as complicated as you want. I could have 15 things inside the argument. It would not matter. I would do it one step at a time until I end up with an answer that I consider simplified. It's simplification that's hard. It's the algebra that, in simplifying, that becomes the most difficult part of the problem. About 16.
Would it be e to the x 1 over x plus e to the x?
E to the x what? Plus or times?
Times. Then plus.
What's the last part of it? The rest of the product rule?
Then you have plus e to the x natural log to the x.
Of x, yeah. So that e to the x can go in place of that numerator, and I have e to the x over x plus e to the x natural log of x.
Does that simplify to x natural log x?
No. I could factor out an e to the x from the top. So what does that give me? If I factor out an e to the x from the top, I've got 1 plus natural log of x. So that's my numerator, all of x. So that is also correct, but not really any more correct than that. It's not really simplified. It's just factor. In other words, if I had some number of e to the x's in my denominator, then there would have been a real good reason for factoring that out, because I can simplify it further. But factoring it out, just to factor it out, you don't need to do that unless you can simplify it.
Okay.
Okay? So it's just a question of figuring out which rules you're going to apply. About 17. There's no better practice for differential calculus than doing these kind of problems. If you can get through these kind of problems, you're in good shape.
Okay.
If you don't understand a lot of the more esoteric stuff about functions and concavity and things like that, just to be able to find the derivative of a complicated function is a good skill to have. That's going to take you a long way. Okay? I want to make sure we do 19. So let's do 19 next. And then we'll go back and do 17.
Okay.
Because 19 looks different than any of the others, right? If I asked you which one you can't do, 19 would have been pretty high up on your list. Okay. So what's the derivative of the outside?
It just makes it, it's 1 over line of x, natural log of x.
And what's the derivative of the inside?
1 over x.
So I'm going to multiply that by the derivative of the inside. What I get is 1 over x natural log of x. And I could also write that 1 over natural log of x to the x power. And that might be the preferable answer, although this has to be just as good. It's just, you don't see this very often, where you have x to the x power. But you don't necessarily need to put it into that format. Okay, so that wasn't as hard as it looked. It's actually pretty easy. Just follow the rules. Take the derivative of the outside, multiply it by the derivative of the inside. In fact, that might at first glance look like you need the product rule, but there's no multiplication taking place there. That's the natural log of, not multiply, but of the natural log of x. Whereas 17 does involve multiplication. So let's do 17.
Okay, so would I take the derivative of...
Always start with u. That thing is always u. That way you don't have to make any decisions. Okay? If you can do it in either direction, which you can, then you have to make all these decisions before you get started. That's why I'm convinced that's not the way to do it. I'm convinced that you should always do, if y equals uv, then y prime is always uv prime plus u prime v. Always do it in this order, because anybody can start with that with no knowledge, skill, or anything else. So you always get the first thing right, and then you take on the v prime. Okay? So what's the first thing going to be?
Sorry, I spaced out there.
Which u?
I don't know.
That's u, that's v.
Okay.
Right? Because it's in parentheses.
Mm-hmm.
That whole thing is being multiplied by natural log of x. So there's u, v. So now go to that and fill in everything. What's u?
X squared plus u.
X squared plus 1.
Yeah.
What's v prime?
1 over x.
I don't have to write it like that. I can just stick the x there. You understand that? In other words, just to start the simplification process. And then what's the rest of it? What's u prime v?
X squared plus, no, 2x times natural log of x.
That is an answer. I can't really simplify it any. Maybe I could a little bit. I could find a common denominator. Let's talk about this, because this is the hard part, the algebra part. Here's what I'm going to do. I'm going to add this fraction to that. The way I'm going to do it is by finding a common denominator of x. So I'm going to write this with an x down there and make sure that x is squared. You see I have not changed the right fraction at all? Okay. Now I can operate on the numerators because I have a common denominator. So the numerators become x squared plus 1 plus 2x squared times natural log of x all over x. Now, for some reason, I was thinking I could simplify that. I can't really simplify it. I cannot combine this x squared and this 2x squared, because this 2x squared is multiplying natural log of x. So I thought I could when I first looked at it, but now upon second glance, I can't really simplify that at all. I can't factor out an x even, because I got this plus 1. In other words, every term doesn't have an x in it. That plus 1 has no x. So it'd be nice if I could factor out an x, because then I could cancel it out with the denominator. But I can't. So there's no real reason to do that other step. In other words, let's back up here and erase that extra numerator or extra exponent that I gave it, and leave our answer like that. It's just 2x times natural log of x. So that becomes our answer. You do not have to take it to there. Same answer, but not necessary to do all that work. Problem is, you don't always know. In other words, sometimes you do all the work and you realize, oh, this simplifies down to the number 1. But you don't realize it until you get to the final answer, and then you realize, oh, I can't really simplify that at all.
Mm-hmm.
All right. We know how to do 18, right?
Yeah.
In other words, it's going to be 1. In other words, we're going to ignore the absolute value sign until
Because that value doesn't mean anything.
tells me otherwise. That would be our answer. 2x over x squared minus 1.
Okay.
Done 19. Let's do 20.
Uh, 21 or 20?
20.
Would you be applying the product rule?
No? I'm going to do the chain rule exclusively.
The chain rule twice, right?
Nope. What's the derivative of the outside?
It just puts it all under 1.
Now we got to do the derivative of the inside. So what is the derivative of cosine squared of x?
Well, isn't cosine squared of x equal to cosine x then squared?
We do have to apply the chain rule twice.
Mm-hmm.
In other words, we've got the derivative of the outside, but now the derivative of the inside requires us to come up with another inside. Well, let's say I'm just differentiating this, okay? That's our y, and somebody says differentiate that. So what's dy dx going to be?
Sine.
First of all, you have to figure out what the inside is.
The inside would be cosine x.
Good. So apply the power rule to the outside.
It would be 2x cosine x.
Just 2
cosine x.
X. I take away 1 from the exponent. In other words, that's just the power rule. Okay? Now I got to multiply that by the second inside, which you said was cosine x. What's the derivative of cosine x?
Negative sine x.
And like I said before, the biggest danger here is misinterpreting that to mean subtraction. Therefore, I rewrite it and put that negative sign in front of the 2, and now I have an answer that can't be misinterpreted. And I could simplify that if I wanted to.
Mm-hmm.
That happens to be the sine of 2x, or 2 times the, no, that's the negative sine of 2x. In other words, using the double angle identity. The sine of 2x is 2 sine of x cosine of x.
Okay.
Okay, but you'll notice we did have to apply the chain rule twice. We had 2 insides. Our first inside was that, the argument of the natural log. And then our second inside was that cosine of x, which is the inside of that function on its own. So I believe this is the first time we've had to apply the chain rule twice.
Mm-hmm.
And you can apply it as many times as is necessary. And I'm convinced that this is the reason why the rule doesn't say the derivative of the inside times the derivative of the outside. Because when you have multiple insides, that's hard to do. You can't do the insides first. You kind of have to do them after you do the outside. And so that's why the rule is the derivative of the outside times the derivative of the inside, even though on 90% of the problems where there's only one inside, it would make more sense to do the derivative of the inside times the derivative of the outside. It comes out looking better if you do it the other way. But when there's two insides, it doesn't make any sense. I mean, I suppose it does. You could do the second inside, then times the first inside, and then times the derivative of the outside, but that's what you'd have to do.
Mm-hmm.
All right, let's see. Let's have a look at 21. Yeah, you know what? You're pretty good on these. Should we go elsewhere and find something a little more difficult?
Okay.
Okay, let me scroll down here. What's your assignment? I mean, we got all kinds of pages here. Let's take a look at some of these type of problems. Find the derivatives of the following functions. Okay, the one derivative we have never talked about is not the derivative of e to the x, but the derivative of some number other than e. In other words, the derivative of a to the x. Okay, if I have, let me take a picture, and I'll show you a way to remember this. If I have y equals a, which is some number just like e, it's just not e to the x, well, the derivative of that is not a to the x. The only function whose derivative is exactly the same as itself is e to the x. But what the derivative is a to the x times natural log of a. Okay? Now, the way you can memorize that is, let's say a happened to be e. And I know the answer is e to the x, but how would I get to it using this formula? Well, my y prime would be e to the x times the natural log of e. Well, the natural log of e is 1. So this shows me that I have remembered the formula right. And this has always been a hard one for me to remember, just because you don't do it that often. You don't do numbers other than e. So what's y prime here? For 23.
Would it be just natural log of 8 times 8 to the x?
Yep. Now notice that looks a little funny, writing it like that. So the way I would write it was I would put the 8 to the x there, and then natural log of 8 there. Which is a bit odd because natural log of 8 is a number. That's all it is. Okay? And so what I'm suggesting here is you put the coefficient after the function, not in front of it, only because when I write it like that, man, I don't know if I'm taking the natural log of 8 times 8 to the x, or if I'm taking the natural log of 8 and multiplying the whole thing by 8 to the x. I mean, you could easily misinterpret that. Whereas if I write it like that, there's no misinterpreting it. That is 8 to the x times that number, natural log of 8.
Okay.
Okay.
And then what would 25 be?
Well, it would be 5 times 4 to the x times natural log of 4.
Does that 5 just doesn't?
No,
Does that 5 matter?
I'm not positive of that. You ask a very good question, and we can figure out what the answer is by applying the product rule. Let's see if we get the same thing. That's what I think the answer is.
Okay.
Okay. But let's apply the product rule. In other words, we have 5 times 4 to the x. So apply the product rule. Y prime would start out being u times the derivative of v, and the derivative of v is 4 to the x times natural log of 4, that's the derivative of v, plus the derivative of 5 is 0, so this all is nothing. So that is our complete answer, and that agrees with what I thought it was.
Mm-hmm.
So yeah, the way to do this is to just pretty much ignore the 5, but don't throw it away, bring it in, and just deal with that. Just like you would if I said, what's the derivative of 5x? You would ignore the 5, you would get rid of the x, and you'd be left with 5.
Okay.
Okay, so coefficients, you can frequently just, you don't have to do anything special with them. But if you ever have any question as to how to treat that coefficient, treat it as a function. Y equal 5, that's a u. And I can apply the product rule. You don't generally have to do that. It's a lot of extra work to apply the product rule. But you can certainly verify if you're doing a problem correctly by applying the product rule. Now, how about 24? What's y prime going to be?
It's just going to be natural log 5 times 5 to the 3t. Or the other way, sorry.
Okay, but you've left out something. The chain rule part of it.
How is the chain rule involved in this?
Because that's an inside right there.
Oh, it is?
Uh-huh. In other words,
Okay.
if I had y equal 5 to the u, then I could certainly figure out what dy du is. That's going to be 5 to the u times the natural log of 5, right?
Mm-hmm.
But I didn't figure out dy dx. I figured out dy du. I got to figure out dy dx also in order to come up with dy dx. I got to figure out du dx. Well, u was 3t, so u dx is 3. So that's the derivative of the inside. I got to multiply the whole thing by that 3. So that's all. I just added a 3 to the front of it because I had to take the derivative of the inside.
Okay.
Okay? Always remember, if it doesn't say 5 to the t or 5 to the x, then there's more to be done. In other words, the first one said 8 to the x. No inside there. Or at least if x is the inside, the derivative of it is 1. But
wait, so if x is an exponent and it's negative, would it count? Would you have to do the chain rule to it?
no, let's do 26. Because what this means is 1 over 4 to the x power. So if I rewrite that, I'm going to rewrite it like this. Now I got to apply the quotient rule.
Oh, okay.
I cannot handle this in that format because it's not really in the numerator. It's in the denominator.
Okay.
I cannot apply the power rule. And I also, you're actually right. I could apply the chain rule to that. Let's just look at that. If I had y equal 4 to the minus x, and I say, well, y prime must be equal to 4 to the minus x times the natural log of 4 times the derivative of the inside, which is minus 1. So is that the same answer as I get?
Yeah.
I think it is, because if I had 1 over 4 to the x, and that was y,
don't know what it is.
Now I would have to apply the quotient rule.
It's just a neat logo. And
I gotta think it has to be the same. In other words, I can treat that minus x as an inside, just like I treated 3t as an inside. Okay? So without spending our last 10 minutes doing this two different ways and proving that they're the same answer, let's just accept the fact that I could do that either using the quotient rule, and the quotient rule is not going to be that tough. I'm just going to have sine x over 4 to the x. Quotient rule will be pretty easy to apply. Whereas applying it in this format, I got the product rule. I'm still going to have to use the product rule. And I'm going to have to use the chain rule on that. So I'm not sure that that's necessarily an easier method. Let's watch how easy the quotient rule is going to work. That's our function. Now use the quotient rule on that. What's y prime equal to?
That would be sine of x times.
Always start with the bottom.
Okay, so it'd be.
In other words, unless you have an easier way to have it memorized, there's no shorter way to memorize it that I can think of that other than you start with the bottom and you end with the bottom squared. That's about as short as it can get. You agree?
Yeah.
Okay, so let's follow that every time. Let's not start with the top, which is what you did. We're going to start with the bottom. That's the first thing I'm going to write is the bottom.
Okay.
Now, it has to be multiplied by the derivative of something, must be the derivative of the top.
Mm-hmm.
And then I'm going to subtract, because order matters. Now do it the reverse. I didn't leave myself enough room. Here, let me do it down here. Y prime is going to be 4 to the x, that's the bottom, times the derivative of the top, minus the reverse. Now take the derivative of the bottom.
That would be natural log of 4x. No, natural log of 4 times 4x.
Okay. 4 to the x times natural log of 4. That's the derivative of the bottom times the top, not the derivative of the top. There's the top. All divided by what?
4x. 4 to the 2x.
Correct. And another way to write it, and you're going to see why I want to write it like this. 4 to the x times 4 to the x is because notice my numerator has a 4 to the x that can be factored out everywhere. So I can take that, cross that, and cross one of those out. Now what I'm left with is y prime is cosine x minus natural log of 4 sine x all over 4 to the x. And there's it doing the quotient rule. Now, I didn't find that too terribly difficult. Whereas if we try applying the product rule and the chain rule, I think it's going to be about the same level of difficulty. I don't think it's going to, you may not have that last step of algebra that we had, where I crossed out the 4 to the x from the numerator and 1 from the denominator. I suspect with the chain rule that you won't have that issue. So it might be slightly easier using the product rule and the chain rule, but we should get exactly the same answer.
Okay.
All right, let's go on. Pick another one that you want to do. We've got maybe only time for one, maybe time for two.
I was wondering if we could do 32, actually.
Okay. Is that the next page?
Mm-hmm.
Is it?
Yeah.
Okay. Yeah, we might have time to, I don't know if we'll have time to do the whole thing, but we might. Here, let me blow it up so I've got some writing room. Yeah, this just looks hard. This isn't really going to be that hard, I don't think. Usually just putting it in the form of a word problem makes people freak out and panic. What they're really doing is giving you a function. There's the function. Okay? Now, it says this equation can be solved for m to define the magnitude of a given earthquake. Okay? Given the magnitude of an earthquake. First of all, this paragraph here isn't quite right. It says this equation can be solved for m to define the magnitude of a given earthquake. Okay, as long as they give you E. I can't solve this function for m at the moment because I don't know what E is. If you knew the energy of the earthquake that was released, then you could solve for the magnitude, m. But they need to give you E, and they don't mention that in that parentheses paragraph there, and they should. It is a refinement of the original Richter scale created by Charles Richter in 1935. Okay. Compute the energy released by earthquakes of magnitude 1, 2, 3, 4, and 5. Plot the points on a graph. Join them with a smooth curve. Well, that's a calculator problem, right?
Mm-hmm.
In other words, when you substitute that for m, you're going to have 25,000 times 10 to the 1.5 power. That's just a number. When you substitute 2 for m, you're going to have 25,000 times 10 to the third power. You with me?
Yeah.
Okay. When we graph all of those and join them with a smooth curve, we're going to see a log graph, because that's the way this works, is using logs. In other words, if I really wanted to solve for m, I've got to get that exponent down in front and use logs to solve for m. I can't move that exponent down in front until I've taken the log of both sides. So that's how you solve for m, is using logarithms. That's how you solve all exponential functions. And by that I mean where your variable is in the exponent. The only way to solve those is using logs. Take the log of both sides, move the variable down in front. Now you have an algebraic equation.
Okay.
Okay. Now, we don't have time to come up with answers for all 5 of these points, but because I know that Richter scales are based on logarithms, basically a 9-point earthquake is 10 times bigger than an 8.0 earthquake, which is 10 times bigger than a 7.0 earthquake.
Mm-hmm.
So every number is a factor of 10 greater energy. In other words, level 8 on the Richter scale earthquake releases 10 times the amount of energy as a level 7. Although this does say it's a modified original Richter scale. So this might not be a straight logarithmic, might not be the natural log of m that I'm going to calculate here. But you can see the horizontal axis is m. The vertical axis is going to be E. And actually, this is going to be exponential in nature. In other words, when I have a magnitude 1, it's 25,000 times 10 to the 1.5. Let's call it that point right there. When I have a magnitude 2, it's times 10 to the third. So I'm increasing exponentially. So my curve has to look like an exponential curve. The greater the magnitude, the more energy that's released, and I end up with an exponential graph. In other words, if we did the exercise exactly as they're suggesting, this is what it's going to look like, what I've drawn here.
Okay.
With various levels. In other words, you're going to come up with an energy level at magnitude 1 and an energy level at magnitude 2 and 3 and so forth. But it's going to look exponential in nature. Now compute the derivative of the energy with respect to m and evaluate it for m equal 3. And what that's going to give me is the slope of the tangent line right there.
Oh, okay.
Okay? Remember what derivatives are. Derivatives are slopes of the tangent line of the original function. Now, DEDM, I'll do that real quick because we only have 1 minute. That's going to be 25,000 times 10 to the 1.5 m times the natural log of 10 times 1.5, the derivative of the inside. So that is what DEDM is. And if I evaluate that at a value of 3, then I get 1.5 times 25k times 10 to the 4.5 times the natural log of 10. And that would be the slope of the tangent line when the magnitude is 3. And that is a number. That's a number, that's a number, that's a number, and that's a number. Multiply those 4 numbers together, you get the slope of that tangent line. And it's steep, very steep. Not the way I've drawn it. I've drawn it with a slope of about 1. It's more like on the far right side of the exponential function, very steep slope.
Okay.
All right, let's call it a night. Jake, that's good stuff. I like the progress you've made on your differentiating these complicated functions.
Thanks.
Yeah, no, and your tests are going to have lots of those kind of questions, I believe. Not necessarily the AP exam, but your exam for your class.
Okay.
Give you lots of those, as opposed to the AP exam, which doesn't give you nearly as many of those as you want. You know what I mean?
Yeah.
Because once you get good at those, you're not afraid of them anymore, and you want them because you know how to do them. Whereas some of the word problems become harder, especially on the AP Calc exam.
I got you.
I will talk to you next time. What's this, Tuesday? I guess next time is Thursday.
Yeah, all right.
Talk to
I'll see
you
you later.
Thursday night. Bye-bye.
Bye.